All right, we will be presenting nuclear fusion. My name is Dylan.
My name is Radu.
That's Michael.
So, nuclear fusion is a chemical process by which two atoms are combined and they make a larger atom. And this process releases a lot of energy. And reactors that harness this process can be made of several different types of elements. This condition of fusing two atoms together is achieved at high temperatures and very high pressures. You need a temperature of about 180 million degrees Fahrenheit or higher, depending on the method used. Additionally, hydrogen is generally used to make a plasma at these temperatures, and then pressure is used to make atoms collide. When this collision in turn fuses them together and forms a new nucleus, thereby releasing a form of energy like heat or a high energy neutron. And the way energy is released depends on the particular method that's being used. There are several benefits to this process. Nuclear fusion has the highest energy density of any fuel source. That means that compared with any other fuel source, you need relatively little mass of fuel to get very, very high energy yields. Additionally, the fuels for certain types of fusion reactions are hydrogen based, and as a result, are much more abundant than carbon used in current mass energy production. Moreover, sourcing such hydrogen fuels does little damage to the environment because you can often get it even from seawater itself. Finally, there's no meltdown risk of the kind seen in a fission reactor, where in a fission reactor you have long-term radioactive effects, such as, for example, in Chernobyl or Fukushima plants. And with a fusion reactor, you don't have that. You certainly have damage and explosions, but you can immediately go in and repair the damage and prevent, fires and things like that. Now, fusion has an important role in addressing climate change. First, there's no CO2 generated by this energy process. And this is extremely important and very, very beneficial because we can have an energy process that generates potentially more energy than carbon fuels while having none of the CO2 effects. Additionally, less land is needed for this particular energy source relative to other clean energy sources such as solar or wind. Finally, this particular process could replace both fission and fossil fuel as a baseline in energy consumption.
So the traditional ways of looking at fusion is starting off with a proton chain, which is how it occurs in stars. So not how they would have achieved in reactors, but that starts off with a proton and a neutron fuse into deuterium. Deuterium fuses with proton to make helium. Then two heliums collide to make beryllium 6. Beryllium 6 decays to helium 4 since 6 is unstable. So now getting into how reactors are traditionally thought of, you start with a deuterium reactor, which is just where two deuterium collide into helium and then one neutron is released. And deuterium can be retrieved from sea water, but it is still considered a rare resource. And then another way that's normally thought of is a tritium deuterium reactor, which is where deuterium and tritium collide to make helium 4 and a neutron. Tritium is not natural on Earth, so it would have to be created in a different reaction. So a newer method of thinking of boron or of fusion is boron fusion. This is the method that was created by or thought of by TAE, and the reactor for this was actually created by them, or one they believe will work in it, since no official working method or reactor has been created. But it is a preferred way because it creates no radiation, so there was no neutron released in these reactions. And the downside is it needs 5.4 billion degrees Fahrenheit over the 180 of the traditional ways of thinking about it. And TAE has made a reactor they believe can last these heats, but once again, it has never held a fusion reactor, so it's not for certain. And then we still need to find a way to actually get the material up to that heat inside the reactor. So now, one proposed method of a reactor is using magnets. So microwaves and ion beams would be used to heat the hydrogen in a plasma inside the vacuum chamber. And then a magnet is used in the center or around it to create the pressure needed for hydrogen to then fuse together. And then the energy is created through the heat is caused by this reaction would heat water and the steam would turn a turbine. And then cooling features would be needed since the immense heat could damage the magnets and the material. Another proposed way is internal confinement, which uses a laser. So now the laser is focused on a single point along a chamber. And then in the target chamber is where the pellet of tritium deuterium is. And then the laser would heat the pellet into the plasma, and then it would also compress it until fusion occurs.
So in terms of the maturity of the technology, there are two major research facilities currently underway. The newest one is MIT's Spark. This is funded by MIT in coalition with a private company that is an offshoot from MIT, as well as private donations and US federal grants. It would be the first reactor to use high temperature superconducting magnets, called HTS magnets, which are still in development. And it would be the first to achieve burning plasma via these magnets. And what that means is that it would create a self-sustaining fusion reaction, which would only require input of more fuel, not more energy, rather than more traditional reactors, which needed a constant input of energy as well as input of fuel to maintain the reaction. This reactor will have between 50 and 100 megawatts energy output with a Q factor of greater than 2, possibly greater than 10. What that means is that it will have at least 2 times the energy output of the energy input. So the energy input for this would be at most 25 to 100 megawatts of energy to get 50 to 100 megawatts output. And following the hypothetical success of this reactor, there would be an electric plant produced with the same technology, and they assume that would be on grid around 2035. Another reactor currently under construction is called ITER, and that is one that has been under construction and in the process of developing a lot of the fusion theory for multiple decades now. It's sponsored by multiple nations with parts being constructed internationally, as you can see in the bottom right. It will be significantly larger than Spark with a 500 megawatt production and a planned Q factor of 10. So 550 megawatt input required for the 500 megawatt output. And it is attempting to achieve burning plasma, but it's using older technology because it's been under construction for a longer time and requires more construction because it is so much bigger because of that older technology. It will be finally constructed by 2035, but they plan to initiate testing in 2025 using only deuterium-deuterium fusion, not deuterium-tritium, until the final construction is completed. In terms of specific technology, the HTS magnets for the Spark are not yet produced at the necessary size, though at a smaller size, they have been produced with a magnetic field 6 times stronger than needed for the spark. In terms of tritium breeding, which was mentioned earlier, both Spark and ITER plan to use lithium-6 to breed tritium in the reaction to prevent the need for continuous production of tritium outside of the reactor and to make the reactor more economical. But this has not yet been used in a large-scale reactor. And all Q values that I mentioned earlier are entirely speculatory. No researcher has achieved any Q value higher than 0.67, so less output than input, and that was in the jet reactor in the 1990s. Additionally, no electricity has been produced by a fusion reactor. All reactors have been solely for research. Moving to costs, the estimated cost of ITER is $22 billion. A study done by the U.S. Department of Energy estimated it to be over $100 billion when discussing the funds they would donate. But an upside to fusion is that only 1 to 200 kilograms of deuterium and tritium each would be required for a 600 to 1,000 megawatt reactor. So that's very low fuel costs relative to other energy sources. It would require roughly $140 per megawatt in subsidies to be competitive, but that's comparable to wind energy and actually significantly less than current solar energy. And you can see the cost of ITER broken down on the bottom right. So magnet technology is the highest cost in developing these reactors, which actually means that they will go down in cost in the future as the magnet technology becomes more advanced and more easily accessible. In comparing the costs of fusion to other common energy sources, on the left you can see the capital investment, and fusion is all the way on the right with the highest capital investment, and on the graph on the right you can see the total cost of energy, so that's the dollars required per megawatt hour of energy or of electricity, and fusion is actually the second lowest after fission, and significantly lower than solar or offshore wind, though fairly comparable to onshore wind. Finally, the criticisms of fusion. It's commonly misconstrued as a universal solution to energy because cold fusion was sought after for so long, which would be fusion at room temperature rather than 180 million degrees. And that is an easy idea to attack because it is in no way currently possible. And it's commonly disparaged by proponents of other clean energy, such as Elon Musk, who is a big proponent of solar and wind energy, who in this tweet is saying that he suspects the best case for solar would be more costly than wind and solar, aka a big fusion reactor in the sky. That's not what it would require based on the current plans, but this is an easy attack to make. So another criticism is that tritium breeding with lithium is inefficient, with a waste of up to 15% and unproven at any significant scale. Additionally, the Q value that I mentioned earlier on the ITER and Spark does not take into account the energy required to maintain the reactor, only the energy required to initiate and maintain the reaction. So it doesn't factor in pumping the water to cool the magnets. It doesn't factor in the water consumption to cool the magnets, which is on the scale of coal reactors, which lowers its environmental benefits. And it doesn't account the massive costs required to create the reactor, including the very high cost on the environment by using fossil fuels to create the reactors. And so, in conclusion of the criticisms, just because it is better than coal and that it's better for the environment does not mean that it's better than solar and wind, and that is its biggest competitor, not actually the traditional fossil fuels. And here we have our sources.